Okay, so what's going to happen now is I am going to give you a region. Okay, just like this whole entire chapter, I give you a region and you do something with it. First, we started out with area. Then I gave you a region and we rotated it. Okay, and now we have the ability to rotate vertically or horizontally. Now I'm going to give you a region and it's going to stay there, but we're going to have a three-dimensional figure that's popping out of the region. Okay, so here I have a region. It's y equals x squared and the x-axis and x equals 1. And sitting inside, like these green things, these are all semicircles. So we have this strangely shaped region that is like curved on top, where every single slice of bread is a semicircle sitting in that region. Or here, every single slice of bread is a rectangle. Okay? So I'll come back to this picture, but I want to show you this right here. So I have this green region, or this green curve, and I have this red curve. Okay? And right now I have equilateral triangles that are popping out of that region. So as I go through here, you can see how the slices change based on where it is. Okay, we could change these. Sometimes you may see squares. Okay, so here's a region where all of the bases, squares are popping out. So the size of the square depends on how far apart those curves are from each other. You see that? Okay. You might see triangles, like a right triangle. Okay. There are all the different slices. And then, like I was showing you before, a semicircle. Okay. These might be the most, the easiest to visualize, right? Here's a region with semicircles. Okay, popping out of it. So then the size of the semicircle is dependent on the distance between the curves. Okay, so our shape changes depending on how close our curves are together. So the closer our curves are together, the smaller the shape that's popping out. The further away they are, the bigger the shape is. So our three-dimensional figure looks kind of wonky.
Okay, so I get like semicircles. So like we have a triangle, there's three functions.
No.
Like the two and then
Okay, that's a really good question. So let's go back to these triangles. Okay. So what we know is we know the distance between function 1 and function 2. So right now this is in a three-dimensional space. But if we just look at like the x and y axis, we know how to represent the distance between two functions, top minus bottom or right minus left. Okay? So if we can figure out that distance and we know the base of our shape, then we can build the two-dimensional shape from there. Okay? It's an equilateral triangle. We know how to find the area of an equilateral triangle. Work. Mm-hmm. Mm-hmm. Yeah.
So I can understand like the point of like rotating it or rotating it or whatever. What is the point of this? Like what we do with it?
Well, here again we're probably talking more about like maybe like architecture, engineering type stuff, where we would want to build some sort of model based on curves. Okay. I don't know if I can give you like a super specific moment where this would happen, but in my eyes, like in like an architecture or engineering type thing, would where we're working with structures would be something that I could see being useful. Okay. So coming back to what you were asking about, okay, as long as we know what the base, like how far apart the base is, we can build the three-dimensional figure from there. And if we can figure out just in 2 dimensions what the area of a cross section is, we can add up all of those areas together. Okay? And if we have like super thin triangles that we find the area of and we add them all together, then now we have 3 dimensions. Okay? So the way that we're going to do this using calculus is we are going to take the area and add them all up using an integral. Yes.
So would it be possible, like, can you technically do any shape just as long as the scale remains consistent?
Yes. Yes. We could do any shape. Okay. So you see this A of x. A of x is going to be our area, and dx is the thickness of that 2-dimensional figure that we're thinking about. Okay. So that is how we're getting our 3 dimensions. We're taking area times thickness. So basically we have a prism, right? Area of the base times the height. Okay. We're taking area of the base times thickness, and we're adding them all together. Okay. We can do this in terms of x or y. So they will tell you that your cross sections are perpendicular to the x-axis. That's how you would know we're using x. If they say that your cross sections are perpendicular to the y-axis, you know you're using y. You're also going to be drawing those rectangles so you can see if the thickness is dx or dy. Okay? But we're taking area times thickness and adding them all together. So we're adding together all of those slices of funky shaped bread. Okay? So this is what I would expect you to do when given one of these examples. So what I want you to go ahead and do is you need to write down the region. Y equals x plus 1 and y equals x squared minus 1. Also write down cross sections perpendicular to the x-axis, so you know that we're setting them up in terms of x. And then go ahead and draw that region. Looks like this. This intersection point right here is pretty obvious. This is the coordinate 1, 0. But what's this intersection point up here? Okay, so we have our region, and we want cross sections perpendicular to the x-axis. So I'm going to draw in my rectangle, and we have thickness dx, which is telling us that we need to do this in terms of x. Okay? So first of all, we have squares. Okay? So here is my region, and what's happening in my region is we have squares where the base of each square matches up with these rectangles that we have drawn in our region. Okay? So imagine taking this square and it's popping up out of the page. Okay? All right. Well, how long is the base of our square? Well, if our rectangle is right here, we know that its length is this function minus this function. Okay? So our base is x plus 1 minus the quantity x squared minus 1. So we have top function minus bottom function. Okay, so that's step one. Well, I guess step two. Step one, draw your picture. Step two, draw your shape and figure out the base of your shape. Okay? Now let's take that information and actually figure out the area of any given square. Okay? Oh, and how do we find the area of any square? Side times side. So side squared, would you agree? Okay? So the area of a square is side squared. So our area would be our side squared. So in your formula that you wrote down, like this would be the A of X that I was referring to, because that's the area of your figure. So then the volume of this three-dimensional funky shape is the integral from 0 to 3. Oh, no, not 0, not even 0. How about -1 to 2, because those are our x coordinates. We're going to take our area, and then dx is the thickness. That's how we get that third dimension. And the integral is adding all of those prisms together for a total. Ellen, what did you say? Wasn't that too bad? Okay. It's not bad yet. I mean, it's really, the only thing that we're going to have to be careful of is just figuring out the area of the shape. Okay, that's going to be probably the most challenging piece. How do we find the area of said shape? Okay, so I'm going to go through a few different examples of different types of shapes you might encounter. Do we get a volume? Yeah? 2.1? It doesn't turn into a nice number. Just 21. Okay. I guess you weren't rounding when you gave that to me. You got 8.1?
Oh, I have.
Or 81/10 if you wanted that. Okay. Okay. So now we're going to try another example. As long as you don't have a question, you can stop me before I go to the next one. Okay. Now we're going to do one where we're perpendicular to the y-axis. So what I think that you should write down y equals x squared. We're going to be perpendicular to the y-axis, and we have rectangles whose height is twice the base. So everything that I circled or underlined in red would be important information for you to write down in your notes, so that when you went back to look at this example, you knew what the heck you were doing in the first place. Okay. That was, sorry. But there will be cake on the Wednesday before spring break. Okay. So Saturday the 14th would be like your first Saturday of spring break. The 16th, the Monday, would be when we don't have school.
So we have like 2 weeks after this week.
Mm-hmm. Today?
It's her birthday. Happy birthday. Oh my gosh. every morning. No, that's your birthday present.
Okay, so here is our region. I drew it really big because I knew it was small, so I zoomed in. How's that? And since we're perpendicular to the y-axis, I know that I am going to have rectangles perpendicular to the y-axis. That's how we know that, with thickness dy. So let's go ahead and label our curves accordingly. So x equals y, that's fine. And then this would be x equals positive radical y. Okay, so we have rectangles whose height is twice the base. So this rectangle that I drew right here, popping out of it, is a rectangle whose height is twice the base. So this is what's popping out right now. And if we talk about the base of this slice, how long is this right here? How long is the base? Right minus left. So radical y minus y. Okay. Right function minus left function. So radical y minus y. Now, what is the height of this? 2 times whatever our base was. So when we talk about the area of this rectangle, we're going to talk about base times height. So our integral is going to go from 0 to 1 because that's where we have our y values. Okay. The area of each of our rectangles is going to be base times height, and then thickness dy gets us to the third dimension, and the integral is adding those together. Okay. Now, are you okay with how I wrote base times height? Okay. If I take the base and I multiply it times the height, I have 2 times radical y minus y times radical y. The biggest piece of this is visualizing where the figures are and getting the area labeled appropriately. Square, rectangles, those are probably the easier slices to work with. Okay. Did you get an answer for me? 0.067. Beautiful. Okay. Probably our more intense slices would be equilateral triangles and semicircles. So I want to look at a semicircle. Okay. So we have semicircles whose diameter runs from y equals radical x to y equals e to the negative x, and we are perpendicular to the x-axis. Yes. Okay. This is one that you're going to be able to use your calculator on because that's the only way you're going to find the intersection between those two graphs. Okay. So I'm going to give you a moment to graph these and find their intersection so that we can properly label our region. Okay. right, do you have that intersection for me?
426. 653.
And your region looks like this. Okay. So we're slicing perpendicular to the x-axis. So we have these slices with thickness dx. And with each of those slices, the base is the diameter of a semicircle. All right, so Max, how would we describe the length of the diameter?
You would do the top minus
Okay, so e to the negative x minus radical x would be the diameter of our circle. Right, it would be the diameter,
top. Not the radius.
not the radius. Okay, just verifying. How do we find the area of a semicircle? 1/2 pi r squared. Okay. So when we set up the volume of our slices, we have the integral from 0 to 0.426. And inside, we need 1/2 pi r squared, because that's the area of a semicircle. So 1/2 pi r squared. Is r e to the negative x minus radical x? No, you told me that that was the diameter. So to get our radius, we take the diameter and we cut it in half. So here's our semicircle, dx, and then that integral is adding the I don't believe you have very many problems this time. You're looking at like 3 parts that are required from 2 problems. So you have like 71A and like 72B and C or something like that. What I want to see, no matter what kind of problem you're doing, okay, so on Friday's quiz, no matter what kind of problem, there's a region with a rectangle labeled either dx or dy. I'd also like to see your shape in these with your base label. Okay? And then obviously the setup of the problem. Okay? Something I'm going to be picky about on Friday, that dx or dy, it has to be a part of your integral for it to be set up appropriately. Okay? So make sure you're paying attention to those. Okay? Alex, what are you getting for your area or volume, excuse me?
0.03447.
Okay, so you have homework tonight. I am not here tomorrow. But look, this book right here on the very top of my pile, this is the solutions manual. So if there's a problem, like an even problem that you are struggling with and you're not having success helping each other, look it up in here. Go to 7.2 and find the problem. Okay? The sub is going to give you a review. I will post my answers and leave the physical key. Please be helpful to each other since I'm not going to be here. Okay? But I'll be here after school and I'll be here before school if you need to come find me. All right? Okay.
Probably look at you.